All right, welcome back to the Explainer. Today, we're taking a massive leap. Everything you probably studied about electromagnetic induction usually stays safely tucked away on paper as, well, theory. But today, we are stepping right out of that theoretical world and into the physical one. We're talking about those massive multi-10 machines sitting on concrete pads out in substations that actually carry the power for your entire neighborhood. Let's get into it. Section 1. Theory to physical reality. Consider this our virtual teardown. We're literally going to slice open the heavy metal tank of a power transformer to see exactly how its raw materials are engineered. Because think about it. When you transition from a neat little circuit diagram to a physical machine, you're suddenly dealing with thousands of pounds of raw steel and copper. The ultimate engineering challenge here isn't just making the thing work, it's figuring out how to arrange all this heavy, incredibly expensive raw material to maximize electrical efficiency, while, crucially, minimizing wasted heat. I mean, you can't just throw some copper wire around a block of iron and expect it to power a city block without totally melting down, right? So, on to Section 2, core form versus shell form architectures. To solve that exact engineering challenge, utilities and manufacturers basically rely on two fundamental ways to arrange the magnetic steel and the copper coils. Notice how clearly these two architectures contrast here. Over on the left, we've got the core form construction. In this setup, the core is basically just a simple rectangular loop, and the primary and secondary windings are wrapped right around the two outer legs of that rectangle, so the coils are on the outside. But on the right, we have the shell form, which completely flips the script. It uses a three-legged core, and the windings are wrapped exclusively around that single center leg. So the steel core is actually surrounding the windings on all sides, wrapping around them almost like a protective shell. And looking at this, you can really see how that complex steel core completely encases those innermost coils in physical reality. So you're probably wondering, why choose one over the other? Well, shell form provides maximum mechanical bracing and incredibly low stray flux. And that's exactly why it's often used for the absolute largest units on the grid, the ones that really need to survive massive short-circuit forces. Core form, on the flip side, is just way simpler to build and significantly easier to cool down. Utilities absolutely use both, and it depends entirely on the power rating and the specific application on the grid. All right, Section 3, the lamination efficiency gain. Let's zoom in microscopically here, moving from the overall core architecture down to the actual steel material itself. So, quick question for you to chew on. If we need massive amounts of magnetic steel just to channel the flux, why not just pour a solid, cheap block of cast iron or steel for the core? I mean, it seems like it would save a massive amount of manufacturing time, doesn't it? Well, the answer lies in how magnetic fields actually interact with metals. A solid steel core would allow massive heat-generating electrical currents, which we call eddy currents, to just swirl freely inside the metal. It's kind of like eddies at the edges of a fast-moving river. And that is pure wasted energy. To stop this, the core is literally never a solid block. Instead, it's built from incredibly thin steel laminations. Each individual sheet gets coated with a microscopic layer of insulating varnish or resin before they're all stacked together. Slicing the core into these insulated layers forces those swirling eddy currents into tiny, highly restricted loops, which dramatically slashes that wasted energy. It is essentially a free efficiency gain just from how we manufacture the metal. The really crucial takeaway here is that the steel itself is a source of energy loss. And get this, it happens even if the transformer isn't powering a single house. We group these into what we call core losses. That includes those swirling eddy currents we just talked about, and hysteresis. Hysteresis is the actual physical energy burned to force the microscopic magnetic domains in the steel to flip back and forth with every single AC cycle. Because both of these losses depend only on the magnetic flux and the frequency and completely ignore the load, these core losses are exactly why a transformer will just sit there, humming and getting warm while sitting completely idle on a shelf. Moving on to Section 4, winding layouts and coils. We've talked a lot about the steel muscle, so now let's shift our focus over to the copper windings that are actually carrying the electricity. Just like the steel core, the copper windings generally come in two common physical layouts. First up, we have concentric cylinders. This is where the primary and secondary windings are wound as nested cylinders, sitting right on top of each other around the core leg. And this is your standard construction for most typical power transformers. On the other side, though, we have interleaved or pancake windings. Instead of long cylinders, the copper is wound into flat discs and they stack them alternatingly, primary, secondary, primary, secondary. This pancake layout is a huge deal because it greatly improves magnetic coupling and reduces high-voltage surge stress, making it the absolute go-to choice for extreme high-voltage applications. Now, if you're looking at a standard concentric layout, manufacturers use this really clever physical trick. The low-voltage winding is always placed on the inside, innermost, directly against the steel core, with the high-voltage winding wrapped around the outside. This serves two massive purposes. First, it vastly simplifies the whole problem of insulating the high-voltage winding from the grounded steel core. And second, keeping them tight together minimizes the amount of leakage flux that actually manages to escape the core. Okay, Section 5, preparing for equivalent circuits. Now we need to connect all these physical manufacturing choices back to the actual performance calculations that grid engineers have to run every single day. Because, let's face it, a physical machine is never perfect. Every single physical trait we've looked at today introduces an imperfection that engineers just have to account for. Because copper isn't a superconductor, we get winding resistance, which causes copper loss. Because our concentric coils aren't perfectly coupled, some flux escapes into the air, giving us leakage reactance. Because our steel laminations still heat up from hysteresis and eddy currents, we have core loss resistance. And just setting up the magnetic field in the core requires a small baseline current, which we model as magnetizing reactance. Put it all together, and the copper resistance and escaping flux are exactly why a transformer's output voltage actually sags a little bit when you put a heavy load on it. And honestly, that brings us perfectly to our next topic. You now know exactly how a real physical transformer is built, from its laminated core right down to its concentric windings. In our next explainer, we're going to take all of these physical realities, the core losses, the leakage flux, the copper resistance, and translate this multi-ton machine into a simple, elegant equivalent circuit diagram. That diagram will let you calculate exact grid efficiency and voltage regulation with nothing but a calculator. But before we get there, I want you to consider this. If a transformer burns energy simply by being plugged in to maintain its magnetic field, how much power is our global grid wasting right this very second before a single light bulb is even turned on? We'll calculate exactly that next time.